My name is Professor Rad, and welcome to my series of arithmetic videos here on YouTube. Before I made a video about, the mathy stuff that makes up this course, I did want to make just a video introducing myself, introducing the course content to see if this is going to be a right fit for you. So as I mentioned, my name is Professor Rad. I teach math at a community college in upstate New York, and I've been teaching at the collegiate level since the fall of 2009. So I'm doing this for a little while. These videos are for our course for arithmetic. I wrote the book that we use in that class, and I wanted to make these videos to go along with that book so that my students can use them. I did also want to host these on YouTube, though, because I think that education should be accessible to anyone who's willing to put in the time and effort and, the real hard work that goes along with learning. So even if you're not taking a class with me, you can still watch these videos, and hopefully they help you conquer some of your arithmetic fears or, fill in some gaps in your math knowledge. So this is for an arithmetic course, and it is intended for adults. So what we're going to cover in terms of things, like in terms of topics, we're going to look at whole numbers, decimals, negative numbers, fractions. We're going to look at those are our objects for the course, and we're going to add, subtract, multiply, divide them. We'll be looking at some exponents and some radicals. Radicals are things like square roots, cubed roots, ninth roots, those kinds of things. We'll also look at some percentages, equations. We will do a little bit with solving for x, not too much, but a little bit of solving for x, how to figure out formulas, a little bit of area and perimeter. So we're going to look at some squares, triangles, and circles, and rectangles. I forgot to mention just rectangles in general. And and we'll also do a little bit of graphing points on a coordinate plane. So if you've ever seen the x-axis and the y-axis and you put the dots everywhere, we'll be looking at that as well. So those are the topics, the big general topics that we'll be covering in this class. And so why, right? So one of the things that you might be wondering is why do I have to take a math class? Why do we have to learn about these topics? Because everyone has, almost everyone anyway, has a phone these days, and the phone has a calculator that can do all of this stuff. And if my phone can't do it, I can at least ask Google, right? So if I'm reading an article about temperature in degrees Celsius, and I don't know what that means, so I want to convert it to Fahrenheit, just ask Google and it'll do it for me. So why do I need to learn about math? So if you ask math teachers or mathematicians, they'll probably tell you something like, well, math is really good for problem solving. And I remember being really frustrated with that answer back in the day, because I was like, none of these are my real problems that I'm facing in life, right? I'm not buying 45 cantaloupes at a discount of 25%. I don't need to know that. I have relationship problems, friendship problems, family problems, apparently interpersonal problems were big for me then. So just, other things that don't seem to have anything to do with numbers. So here's why mathematicians kind of think math is about problem solving. So my background in math is in a field called algebraic number theory. You might need to bear with me here for a little bit. It is a little bit circuitous, but it will come back, I promise. So in algebraic number theory, you approach math algebraically, and that might mean a little bit different from what you've heard the word algebra mean before. So here's what an algebraic approach means to me. It means that I look at collections of objects, I interact those objects, and then I examine the consequences of those interactions. So to me, that is the most basic concept behind algebra. So for me, those objects might be numbers, right? So 3 and 5. Those interactions might be adding and subtracting. So if I have 3 things and I add 5 things to them, when I add them, I have a total of 8. And if I take 5 things and I add 3 things to them, and I add them together, I also get a total of 8. So whether I have 5 plus 3 or 3 plus 5, the number of fingers on each hand is different, but the total is the same. So that would be an observation about an interaction. So my objects are numbers, the interactions are adding, and an observation is when you add, you can change the order of the numbers. 5 plus 3, 3 plus 5, you get 8 either way. Now, another possible interaction is subtraction. Don't worry, we're not going to do too much more mathy stuff beyond this right now. But another possible interaction is to do like 8 minus 3. So if I have 8 and I take 3 away, I have 5 left over, right? So then what if I want to change the order for subtracting? So I start out with 3 things and now I want to take away 8. There's not 8 things for me to take away. So we have an observation about subtraction that's different from addition. In addition, we can change the order. In subtraction, we can't. So then you have to make a choice. Your choice is, do I just make a rule that says you can only take big numbers minus small numbers? Or do I say, you know what? Sometimes you want to start out with 3 and take away 8. For example, let's say that I'm selling you an $8 item and you only have $3 on you, but you know you have a $5 bill back home. So you want to bring that tomorrow, right? And that'll pay off the whole item. So I need a way to represent that you have given me $3 and you owe me the remaining 5, since 3 plus 5 is going to give me that 8. And that's actually where negative numbers came from. They came from people doing commerce and wanting to represent credits or debts. So in that choice, I had a set of objects, whole numbers, I interacted them, and then maybe I make a choice that, you know what, I want to be able to do 3 minus 8, so I have to introduce more objects into my pool. So that's how an algebraist approaches math, but here's where you might see that in other areas. So think about, like, if you're a chemist. If you're a chemist, your objects are atoms and molecules. Your interactions are things like heating or stirring or cooling, and your results of those interactions are new compounds, bonds that form, bonds that break, things that you want to do, so they make good chemicals, things that you don't want to do because they are poisonous and will kill you, right? So that's one situation where, again, you have some objects, you interact them, and there are consequences. Or maybe you're a mason and your objects are stones and bricks and different kinds of compounds. Your interactions are mixing those things, and your consequences are things like, if you mix too much water with your sediment, you're going to have a soggy cement. And if you don't mix enough water with your sediment, then you're going to have a crumbly cement, right? Or if you are, you know, like nailing 2 things together, you can nail 2 boards together, but you don't want to nail a board into wet cement. It's not going to do what you want it to do. So there's another situation where you have some objects, interactions, and consequences. And not just like things where you're thinking, okay, but those might use math and numbers anyway. Think about like a computer animator. Your objects are the physical, like, objects on the screen. You interact them by shifting them or rotating them or stretching them. And then consequences are that you give believable movement and interactions or not. If you're a poet, your objects are words and phrases and imagery, and your interactions are things like literary devices, like assonance, alliteration, simile, metaphor, that kind of thing. And then the consequences are you have poetry that's got a certain rhythm, or you have images that develop vividly or less vividly. You get double meaning or not, depending on how you interact those objects. So when I think about math in terms of what I do as an algebraist, those higher concepts of what we're training our mind to do through math apply to other places. We just might not think of it in the same way. And this is where the mathematicians and problem solving comes into play. So math is basically like a gym for your brain. So when you go to the gym and you work out on the machines, right? I'm never in my real life going to need to do an elliptical movement, right? Like, I'm not going to stand there and just like stand in place, step on my own foot here, stand in place and do some exercises like that, right? I might need to walk or run, or might need to train my body how to adapt if my heart rate goes up or down, or respond appropriately in certain situations, train my body to be physically healthy. But that actual movement I'm doing at the gym, like, or if I'm lifting weights or something, I'm not doing that specific movement in my daily life, but I'm training my muscles to respond to similar situations and apply them when I meet those circumstances. So your brain is doing the same thing when it studies math. So it's like gym for your brain. That's why it hurts. That's why it's hard. And that's why it's difficult sometimes to just be like, why am I doing this? So you're doing it to improve your brain health and just to think more analytically. So I am going to put a few definitions on the board here because these are important words. So if you're taking the class with me, you want to be writing these down in your notes. And if you're not taking a class with me, but you plan to watch these videos and you want to make sure you know these terms, feel free to grab a notebook and jot them down. All right, so I've written the definitions on the board. I am going to talk about them, but if you want to jot them down, I'd recommend pausing the video and then unpausing, and we'll kind of talk through it. Okay, so analytical reasoning is a way of reasoning. So it's a thought process, and it's built up of two main components. So there's inductive reasoning and deductive reasoning. So inductive reasoning is the process of moving from specific observations to general observations. So when I say like specific observations, that means things like 1 apple, 5 apples, 24 apples. So those are specific numbers of types of objects of apples. And then when I say general, I mean things like apples. So I'm not telling you how many apples there are, just if I take however many apples I have, and then I do this. So specific is a specific number or a specific type of object, and then general would be any, just using a phrase like any or every or all or none, right? Those big all-encompassing words. So you can also think of inductive reasoning as like pattern recognition and using patterns to come to a conclusion. So here's an example of inductive reasoning. So my cat, I have a cat, and his name is Lenny. And so let's say I set an alarm on Tuesday. I set an alarm on Tuesday for 6 in the morning. So I get up at 6 and then I go feed Lenny and then I go about my day. And then on Wednesday, my alarm goes off at 6 again and I feed Lenny, then go about my day. And then Thursday at 6 o'clock, I wake up, I feed Lenny, go about my day. Friday, my alarm goes off at 6 o'clock, I feed Lenny, and then I go about my day. And then Saturday comes, and Saturday, I don't have to get up early, I want to sleep in. So Saturday, my alarm doesn't go off at 6 o'clock. However, Lenny doesn't know that. And he's like, Mom, why aren't you feeding me? At 6 o'clock, it's food time. So he wakes me up. He's going to like walk all over my face. He's going to meow, and he's going to make sure that I get up and feed him. So my cat is using inductive reasoning. He's observing specific instances. Tuesday, he got fed at 6. Wednesday, he got fed at 6. Thursday, 6. Friday, 6. Saturday, it better be 6, right? So he's taking these specific observations and making a general conclusion that every day, doesn't matter what day it is, every day Mom's going to get up at 6 o'clock and feed me some breakfast. So that's an example of inductive reasoning. We're using a pattern or specific instances and making a conclusion about every day or every situation. Deductive reasoning goes the opposite direction. So deductive reasoning takes a general rule. So it takes a general rule and leads you to specific conclusions. So for example, maybe, I don't think this was a rule when I was a kid, but let's just say it was for purposes of this example. So let's say my parents had a rule that said if I didn't do my chores, then I couldn't play with my friends. So this is a general rule because it's applying to all chores, any chores that I needed to do, and it's applying to any people I wanted to see. So that's the general rule, uses anybody, any chore. And then I would apply that to specific circumstances. So for example, maybe today my chore was to wash the dishes. So if I didn't wash the dishes, then I couldn't play with Amy after school. Or maybe my chore was to clean my room. So if I didn't clean my room, then I couldn't play with the neighbors up the street. If my chore is to sweep the floors, if I don't sweep the floors, then I can't go to a sleepover this weekend. So I'm taking these specific chores of dishes, sweeping floors, cleaning my room, and applying them to specific friends. My friend Amy, the neighbor up the street, my friends at a sleepover. So that's a situation of deductive reasoning where you're going from general rule to specific. A place where you'll see this in math classes is like, here's the formula for converting from Celsius to Fahrenheit. And so no matter what specific degree of Fahrenheit you have, you plug it into that formula and it will give you a specific answer. So the formula is the general rule, and then whatever numbers you plug in tell you your specific results. So this is a process of analytical reasoning, and it is used in problem solving. So when you have a problem that you're trying to solve, right, you have to be able to define the components of the problem. So define your objects of the problem and how those components or objects or people are interacting and the consequences of those things. And to solve the problem, so that helps you define what the problem is, that algebraic process of objects, interactions, consequences. And then you want to solve the problem, you can look at patterns of previous or similar problems that you've encountered in the past and apply those, make up a rule to apply those to the search, this situation. Or maybe there are some rules in place, like laws, that prevent you from doing certain things. So if you're solving a certain problem, then you want to take those laws and rules and then apply them to your specific situation. Well, I can't get to the hospital in 20 minutes because I can't exceed 100 miles per hour. So I have to come up with an alternate solution, right? So problem solving is this interplay between inductive and deductive reasoning. Inductive reasoning is often like the inspiration. So you recognize patterns and you come up with a hypothesis. A hypothesis is basically like a rule you think might exist. And then deductive reasoning establishes that rule. So this is the workout at the gym that you're doing for your brain when you study math. You're learning these types of thinking and reasoning processes. And then the goal is you don't think about climbing the elliptical when like you're chasing after your cat who broke off his leash, right? You just go and you do it. So you're not going to be necessarily deliberately thinking of these processes after you've trained your brain to use them. You're just going to apply them. Okay? So this is kind of like the higher order level of why study math. Of course, there are direct applications too. So if you're going into engineering or chemistry or any branch of science, then you're going to need to use these formulas, need to know how these operations work. If you're going into computer programming, you're going to need to know how to take something specific you want to have happen and move it into a general process. So like a for loop has a lot of that going on. And yeah, there's a lot of mathematical thinking that goes into programming. So there's this higher order of thinking, and then there are also direct applications. And I'll try to include those when I can. So there will be moments where I'm like, here's what you're going to see in a future math class. So here's how what we're doing right now with numbers is going to apply when we have X's. Or here's a place where I use geometry in my day-to-day life as a human being who's not a math teacher, right? So outside of teaching, where do I use this? I use it mostly when I crochet, to be totally honest, and that's pretty much it. So there are a lot of direct applications that we'll look at, but really what we want to be focusing on is the why behind everything. Why are we doing this, and why are we doing it this way? Because the why is this analytical reasoning stuff. And then one last why that I need you to think about that's really important is, why are you here? Why are you in school? Why are you working to study this math? So you need to have that so that when the exercises get really hard and you're losing your breath over them and you get really frustrated and want to throw your phone or computer against the wall, please don't do that. But when you do get frustrated with it, you can take a step back and say, okay, why am I doing this? Oh, I'm doing this because I don't understand this Common Core stuff and my kids need help with their homework and I want to be able to help them. Maybe your why is you want to get a better job so you can help your kids, or get a better job, make more money. Maybe your why is you actually know how to do this math, but you need to learn the English words and phrases. So I work with a lot of students for whom English is a second language. So there are a lot of reasons to be taking a course like this one. You need to find what your why is and why it's important to you. And hopefully with that, we can help you to be successful. So, okay, I've kind of babbled for a while here. I'm sure this video is longer than I wanted it to be, but hopefully some of this gives you an introduction to me, how I explain stuff, what I think is important about math, and help to spark some thoughts in you why you think this kind of stuff is important. So next video, we'll start in on some actual like numbers and things. We're going to be introducing ourselves to whole numbers, counting numbers, things like that. So I hope you have a fantastic day. I will see you in the next video, and bye for now.